We now proceed to talk about more on the types of events we have in statistics. You see, you recall that an event is a collection of experimental outcomes or sample points in the sample space of an experiment. So, we want to talk about the types of events in statistics. Sorry about that typo there. Now, first we look at mutually exclusive events. What are mutually exclusive events? Think for a second. Can you, an individual in this class, get an A at the end of the semester, and the same you in this same class get a B in this same class at the end of the semester? I would argue that is not possible. You will only end up with one grade. Yes. So if we talk about two events, say event A, that you get an A in this class at the end of the semester, and the event B, that the same you get a B in this class at the end of the semester. Those two events cannot occur together. They are events that once one occurs, it excludes or prevents the other from happening. Such events are called mutually exclusive events. So, it suffices to say that two events are mutually exclusive if the occurrence of one event prevents the occurrence of the other event. For example, in the toss of a coin once, the event A obtaining a head and event B obtaining a tail, these two events are mutually exclusive in a single performance of that experiment, namely tossing a coin once. You cannot get a head and a tail at the same time. Once you get a head, it prevents a tail from occurring. Once you get a tail, it prevents a head from occurring. So it is mutual in that sense. Then we proceed to independent events. Think about how many steps you have taken today and the number of calories your professor, have eaten today. These two events have no connection. They have nothing in common. These kind of events are said to be independent. Another theoretical example would be to look at the event of obtaining a head. So you toss a coin, obtaining a head, and a die, obtaining a 3. If you toss a die and you throw a coin, or you throw a coin, the reality is getting a head on this coin has nothing to do with getting a 3 on the die. So these events, getting a head in the toss of a coin and getting a 3 in the cast of a die, these two events have nothing in common. They are said to be independent events. Then what about dependent events? As you might already figure out, two events are dependent if the occurrence of one event depends or is affected by the probability of the other event occurring. So, for example, if we are attending a face-to-face class, you coming to class probably depends on your knowledge that I am also coming to class. So, those two events are said to be dependent. The event that you come to class and the event that I come to class. So, you coming to class depends on the event that I come to class. Such events are said to be dependent. Now, let's see some other types of events in statistics on the next page. And to begin, we want to talk about the OR event. So, an outcome is in the event A or B if the outcome is in A only, or is in B only, or is in both A and B. Let's take an example to illustrate. So, we have the sample space of an experiment, that is, the set of all possible outcomes, is from 0 to 9. If we define an event as having the possible points 1, 2, 3, 4, 5, and another event B as having the points 4, 5, 6, 7, 8 out of the sample space. If we are required to find the event A or B, let's see what we do. Using a Venn diagram might be very useful. This rectangle would be a collection of all the possible outcomes. And within it, I'm going to extract or embed the events A and B. So I'm going to draw event A and then event B. For event A and B, you observe that they have points in common. I'm going to start from that. They both have 4 and 5 in common. So I'm going to write 4 and 5 in common. Then what else do I have for A? I have 1, 2, and 3. And what else do I have for B? I have 6, 7, and 8. Then for the entire sample space, what do I have left? 1, 2, 3, 4, 5, 6, 7, 8. I'm left with 0 and 9. I'll position those outside A and B. So we now proceed. What is the event A or B? The event A or B will cover all points in A only, or in both A and B, or in B only. So it has the points 1, 2, 3, 4, 5, 6, 7, 8. And based on these points, we can calculate the probability of event A or B. This will be number of points in A or B divided by number of points in the entire sample space. How many points do we have in A or B? 1, 2, 8. So that will be 8 out of how many numbers do we have in the entire sample space? In the entire sample space, we have 10. So the probability of A or B is 8 out of 10 or 0.8. The next question. Are events A and B mutually exclusive? Does it mean that if event A occurs, event B cannot occur? A mathematical way to check this is as follows. We will check first for the probability of, this will be the first step, of A or B. 2, we'll check for the probability of A separately. 3, we'll check for the probability of B separately. Now, if probability of A or B is the same as probability of A plus probability of B, it follows that A and B are mutually exclusive. So let's check. Step 1, we get the answer for this, which we already have, 0.8. Step 2, we need to check for the probability of A. This will be 1, 2, 3, 4, 5, 5 out of 10, which is 0.5. Then probability of B is another 1, 2, 3, 4, 5. This is 5 out of 10, which is 0.5. So we're ready to check. 0.8, that is here, 0.8. Then probability of A plus probability of B is 0.5, 0.5. So you have 0.5 plus 0.5. This is equal to 1. So on this side, on the right-hand side, we have 1. On the left-hand side, we have 0.8. Since this is not true, it follows that events A and B are not mutually exclusive. So since, let's put this in a different color, since probability of A or B is not equal to probability of A plus probability of B, A and B are not mutually exclusive. I'll shorthand that as ME. They are not mutually exclusive. With that said, we proceed to what we call the general addition rule. You see, for any two events, E or F, that are not mutually exclusive, the probability of one event or the other will be the probability of one event on the one hand plus probability of the other event minus the probability of E, and F. You can check that at your own leisure time for this. This formula is also very useful in the following problems. In this problem, we're given the probability of E, which is 0.40. We're given the probability of F, and we're required to find the probability of E or F. If we know probability of E and F. Following the general addition rule, where the probability of E or F is the probability of E plus the probability of F minus the probability of E and F. This will be equal to probability of E, 0.40, 0.40, probability of F, minus probability of E and F, which is 0.05. So this will be 0.75. This is the probability of E or F. Quite easily done. With that question completed, we proceed to the next example. We would like to find probability of F, given the probability of E or F, and probability of E and F. All we have to do to know that this formula is required is that the pieces we are given all feature as a group in the general addition rule, where you have probability of E or F is equal to probability of E plus probability of F minus probability of E and F. We're given the probability of E or F already in this case. So probability of E or F is 0.90 equals probability of E, that is 0.60. Probability of F, that is what we want to find. We're going to call it X. And then the probability of E and F, that is 0.05. So minus 0.05. So on the right-hand side, collecting like terms, 0.60 minus 0.05, 0.55 plus X. And on the left-hand side, we have a pending 0.90. To isolate our X or solve X, we need to subtract 0.55 from both sides. 0.90 minus 0.55, that gives 0.35, and that is equal to X. Remember, X was a placeholder for the unknown. So it follows that the probability of F is the same as 0.35. We now proceed to further examples. In this example, we're told that the following table shows the distribution of murders by type of weapon for murder cases in a particular country over the past 12 years. We would like to complete parts A through E. Different types of weapons and the probability. The first question is to assess if the given table is a probability model. Why or why not? Step 1, we need to check if rule 1 is satisfied. Each probability here, let's see, is a number between 0 and 1. So rule number 1 of a probability model is checked out. Then for rule 2, we need to add up all of these probabilities and see if it adds up to 1. Let us see. So when I added up all of these numbers, the sum was equal to 1. Since the first rule and the second rule both check out, it means that the table is a probability model. It is equal or the same as a probability model. Question B. What is the probability that a randomly selected murder resulted from a rifle or a shotgun? So this will be probability of rifle or shotgun. In this case, this would be the consideration of the following: rifle or shotgun. So that would be 0.024 plus 0.034. This will be 0.058. We now proceed to question C. What is the probability that a randomly selected mother resulted from a handgun, rifle, or shotgun? So this will be equal to, considering that of a handgun, that will be 0.474, rifle 0.024 plus 0.034 from a shotgun. And that will be equal to 0.532. Then question D. What is the probability that a randomly selected mother resulted from a weapon other than a gun? Well, one fast way to get around this is we know that the total is 1. So if we want the probability that a randomly selected mother resulted from a weapon other than a gun, it means from the whole probability of 1, we can remove all probabilities that have to do with guns. So that will be equal to 1 minus those that are guns. So we have handgun is 0.474. I'm going to combine those ones together. All the ones that come from a gun. Rifle, that will be 0.024. And we have that of shotgun, that will be 0.034. And then you have unknown firearm, which is also another type of gun, and that will be 0.148. So that will be 1 minus this addition. So that will be equal to 0.32. Now we proceed with question E. Are mothers with a shotgun unusual? We need to compute first the probability of mother with a shotgun, and that is equal to 0.034 from the table right here. And next, that'll be the first step. The second step is to check if that probability is less than 0.05. 0.034 is less than 0.05, and so mothers with a shotgun is unusual. This will be the correct answer there.